of organic questions. So this one, name an example of a synthetic polyester in a polyamide. So this one is terylene, and polyamide, that's nylon. Or you can also add Kevlar, that's used in bulletproof jackets. Terylene is for clothes. Polyesters and polyamides are formed by condensation. Name a molecule which is commonly eliminated in such reactions. That's a water molecule. So whenever you have a condensation reaction, a water molecule is often eliminated. So water molecules are eliminated in condensation reactions. The next part is table shows the repeat units of a number of polymers. Place a tick against the ones which is biodegradable. So I'm going to give you an idea about biodegradable polymers. Let me just add one second. Condensation polymers. I'll give you first a very quick brief overview of what condensation polymers are, and I'm going to add this to the notes over there. This thing is just one second. So this is an example of this is one example of a polyamide. This is how polyamides are formed. What basically happens is you have a molecule, and that molecule is a dicarboxylic acid. And this one is actually incorrect. Let me correct this. I'll just quickly explain. I'll quickly explain condensation. Condensation polymers. So very quickly, let's just have a brief overview. So one thing, remember, condensation polymers, there are two types. One is a polyester. Polyesters are formed where you have a molecule, and this could be any molecule. The only thing is it's got carboxylic acids on both sides. So you've got C double bond O, and so you've got C double bond O and OH groups on both sides. So that one is one molecule. And you've got this other molecule that's a diol. So it's an alcohol. So alcohols. So the box it could represent any molecule or whatever. It represents a carbon chain. So this other one is going to be an alcohol. So it's going to have OH groups on both sides. And the two groups are going to just repeat over and over again. And a water molecule is going to be formed between them. So there's going to be a condensation reaction that's going to happen. And the condensation reaction would be that the OH is going to be removed and the H would be removed over here. The OH is removed, the H is removed from the alcohol, the OH is removed, the H is removed. Basically what's going on is that this carbon has a very strong positive charge, and you've got a lone pair over here on this oxygen, and this lone pair is basically getting attracted to this carbon, which is positively charged. So they're getting attracted, in the water molecule in between, in the middle, it's getting repelled. So the H and OH is lost at the end. H is lost. So the alcohol loses the H. The alcohol loses the H, and the carboxylic acid loses the OH. And all of them are going to just add up. And when they add up, I'm going to remove the water molecules from the middle. So H is gone, OH is gone, OH is gone, and the H over here is gone. The H over here is also gone, and they're going to end up forming linkages with each other. So all of them are going to connect together, and they would eventually all bind or link link up with each other, forming these connecting bonds, and that's a lot of ester links. So a lot of ester links are going to be, this is an ester link. So a lot of ester links are going to be produced in the middle, which is why it's going to be called a polyester. So that's the first one. That's the example of the first condensation. So that's your polyester, and the example of a polyester is terylene. That's used for making. It's used in cloth, in fabrics. And the other one is fats are also the natural ones. One of them is synthetic. The other one is natural. Fats aren't really a polyester, but they have kind of the same structure. I mean, poly means lots of them, thousands of them. Fats don't have thousands of them. Fats have ester links, but very few ester links. So you can't really call them polyesters. I mean, for example, here's a fat molecule. So in this fat molecule over here, let's look at this one. So in this fat molecule, you'll notice so now in this fat molecule, notice these ester links. So, but there would be a lot of them. So the word poly would probably not be applied to a fat, but it's kind of the same structure. It's groups connected together by these ester links, which is kind of the same. So that's basically an example of a polyester. It's a dicarboxylic acid. Or any molecule that's got carboxylic acids on both sides, reacting with a diol. Those are your two monomers. And the other one is polyamide. That is kind of almost the same. So what I'm going to do is I'm going to copy the same. I mean, it's kind of the same basic structure. That's how polyamides are formed. So we're just going to change this to polyamide. Or no, Iman, we're doing a past paper. We're just trying to cover the. It's a question on. I mean, the question is about condensation polymers. So we're going to just quickly cover this very quickly. So what's the difference between how do you make a polyamide? In a polyamide, the first thing is the monomer is an acyl chloride. It's got a Cl. It's always an acyl chloride. It's got a Cl. So it's instead of being a dicarboxylic acid, it's actually a diacyl chloride. So this one is a diacyl chloride. And the same thing repeats. Not a carboxylic acid. This one is a diacyl chloride. And the other part is not an alcohol, it's actually an amine. So instead of which, this one over here is going to be a diamine. So it's going to have NH2 groups on both sides. So your two monomers are different. So you're not going to have this. Instead, you're going to have, so instead of an alcohol, in a polyamide, you're going to have, one second. So you're going to have this thing. But the basic idea is the same. The lone pairs on N are going to be attracted very strongly to the positive carbon over here, and you will have an elimination reaction. The Cl and the H will get removed. The H and the Cl will get removed everywhere. So the H at the end is also gone, and the Cl at this end is also gone, and they would eventually end up forming. So you've got a diamine. So this one over here is your diamine, and they're going to eventually all link up. So the Cl is gone. The H and Cl in the middle are gone. The H and Cl in the middle are gone. The Cl and H over here, and so on. So they're all gone. And what you're left with is you're left with. So you're going to just put them together and you're going to link them up. So that is what is going to happen. So you're going to create these linkages between them. The N and C will bond. The N and C over here will bond. This will bond. This will bond with. And remember to draw these continuation bonds always. So that's your amide linkage now. This is what has happened. And this in the middle is your amide link, which is why it's called a. So that's why it's called a polyamide. And examples of polyamides includes nylon, and they include Kevlar. So nylon is used for making ropes, fishing nets, and Kevlar is used in bulletproof jackets. Now, about these two polymers, about polyesters and polyamides, remember, both of them tend to be biodegradable. They tend to be strong as well, and they tend to be biodegradable as well. So polyesters, unlike addition polymers, or sorry, condensation polymers. So your condensation polymers are biodegradable. So they tend to be biodegradable, and they easily hydrolyze. Why? Because the linkages are highly polar. So they're very polar molecules, and they attract water molecule very strongly. So as an example, if I have an ester link, then that ester link would, and here's the box, whatever the molecule is at. And let's just put an R over here. I don't care what's on this side. Let's say there's an ester link. So what happens is, firstly, the carbon is like really positive. So if there's a water molecule around, the lone pairs of water molecule are going to get attracted to this carbon that's positive. Secondly, this oxygen has lone pairs. So the H over here in water, which is the H in water has a slight positive charge. So it's going to get attracted to this oxygen over here. So the bonds will break and it's going to be a very reactive, these linkages are extremely reactive and they tend to hydrolyze very quickly. So linkages are very polar. Heating with dilute acids or dilute alkalis would definitely hydrolyze the whatever the condensation polymer is. So heat with, I mean, that is exactly what happens to protein when you cook it. You just heat it with dilute acid or alkali. For hydrolysis to happen. And the reverse reaction would then happen. The H from water will get attracted to the O and it will form the alcohol back again. The OH from the water will get attracted, which is negatively charged, is going to get attracted to the carbon and it would end up forming the carboxylic acid molecule back again. So they're extremely biodegradable. So the question was all about the same thing. This question over here. The first part was you see water eliminated. So they're asking, is this biodegradable? So that is an ester link. So yes, it is biodegradable. Here's another one, and that is also an ester link. So I mean, that will, whether it's an ester link or an amide link, it's going to biodegrade. This one is an amide. You got a serial bond over and it, so the molecule would eventually break. So that is also biodegradable. The only one that's not biodegradable in this case is option C. Acha, pehle to ye batao ki is the first, I mean, let's look at the first part. I'm going to talk about this later. But is this idea clear that polyamides and polyesters, they're both biodegradable? And the linkages are extremely reactive. Is that part clear? Risha, clear?
Yes, sir.
See, Munia, is this clear?
Yes, sir.
Okay. So that's
Sir,
the.
how are we figuring out what the monomers are in the question?
I said, whoa, I haven't come to that. I'm going to come to that. Okay. They're not actually asking you. They've only shown you the repeat unit. Okay. But I'm going to talk about that. So let's extend this discussion. I mean, although this is not asked in the question, they're not asking for the monomer. Bhaskar, is that clear? I mean, they're not asking for it. But let's assume we want to find out.
They're not asking for it, but then how can we figure out the linkages if we don't know what the monomers are?
No, the linkage is still there. It's right over there. It's an ester link. So the ester link will easily break.
Oh yes.
Okay. So it's going to easily break. So I mean, that's the idea. But I'm going to talk about the monomer as well, because that's an important question. Like, what is the monomer of this thing? So the first thing is, I've drawn these polyamides and polyesters. Now, one important thing is, what's a repeat unit in a polyamide? The repeat unit is, you can start at any point, right? And see where the molecule starts repeating again. And that's this point, right? So that's your end. Like, after this point, the same thing kind of gets repeated back again. But the starting point could be any point, right? Like if you have a chain, a polymer chain, you can start at pretty much any point. Let's start over here. Where does it start repeating back again? It probably starts getting repeated at this point, right? Is that clear? So
yes, sir.
So the representation could vary. For the same molecule, was a repeat unit, that I mean, there's the two ways to show a polymer. That is, one is you draw the polymer, a section of it, or you draw a repeat unit. But the problem with the repeat unit is there are many ways of showing the repeat unit. You could start at any point. If I start at this point, my molecule would again repeat at this point. So that's going to be my repeat unit. So the repeat unit could vary. So let's so this is slightly tricky. How do we find monomers from repeat units? Like I'm talking about the reverse. So how do we do that? So for example, in this question, they didn't actually ask you to do that, but they gave me a repeat unit of a polyester. This is definitely a polyester because it's got an ester link. So if I go back and put it over here, I want to find out what are the two monomers for this molecule. Like how do I know what the monomers are? What I'm going to do is I'm going to extend this a little bit. I mean, remember there's a carbon atom, So I'm going to just draw this in the normal way. So there's a carbon. It's got a CH3 at the top, and right next door there's another carbon, and it's got a double bond O, and then there is an oxygen, right? And over here there's one bond over here. And there's definitely going to be an H because the top one is a skeletal formula. So carbon is not completing 4 bonds. So there's definitely going to be an H. And there's a continuation bond over here. So I've drawn a simplified structural formula of the skeletal formula shown above. Okay? Is this clear? These two are exactly the same thing. Is that clear?
Yes, sir.
Now
Yes, sir.
so now the point is I want to draw the monomer. Remember, a polyester is actually formed from two monomers. So how do I figure out my two monomers in this molecule? What I'm going to do is because it's a repeat unit, I'm going to just start repeating it and start making the connections. So I'm repeating the same thing. It's going to get repeated over and over again. So, and let's get rid of these brackets because. So is that clear? What I've done over here is I'm just repeating the same thing over and over again. So here's another one. I'm going to fix it at this point. And I'm going to just get rid of this bracket. So that is what I've done. Is that part clear? This part clear?
Yes, sir.
Yes, sir.
So this over here is kind of exactly the same. It's kind of exactly the same thing, except now coming back to this, how do I draw the monomers? What I'm going to do is I'm going to break the ester links. Because when a polyester was formed, two monomers joined up and they ended up forming the ester link. So I'm going to do the reverse. I'm going to break the ester link. This O will turn back into an alcohol. This serial bond O will turn back into a carboxylic acid. So I'm going to do the reverse now. So here we go. I'm going to break the ester links. But let me make a copy of this. One second. This is fun. So same thing. I'm going to start breaking the ester links. So that's an ester link that's gone. Here's an ester link that's gone. Ester link is gone, and ester link over here is it's also gone. And now we're going to try and I'll try to separate them. And basically we're getting the same. If I break the ester link, I'm pretty much getting the same thing. Let me just remove a few of them. So all I've done is I've broken the ester link. And if you go back and have a look, if you break the ester link, the acetyl bond O turns back into NOH gets added to it, and H gets added to the oxygen over here. That's what we're going to do. So double bond O turns back into, it gets its OH back. The O gets its H back. This O gets its H back. This gets its OH back. H back, its OH back. So your monomer is this one. So that's your, so that is what your monomer is in this case. So for this question, if they ask you to draw the monomer, make sure this is what you're going to do. Make sure this is what you're going to do. You're going to make repeat units of this, connect them, extend this, and draw and break the ester linkages. Break all the linkages and start adding the OH, H, and OH back again. That will give you your monomer. Is that clear? Is this clear? Yes or no?
Yes, sir.
Alicia, clear? Monia?
Yeah.
Yes, sir. Thank you.
So
Yes, sir.
I'll just do another one, which is again, they didn't ask in the question, but here's the molecule. It's not sure why it's not reading it. Okay, so here's the molecule, and I'm being asked to draw the monomers. Like, which monomers does this have? So this in the middle is your the middle part is your benzene. So I'm going to write it as C6NH4. This one next to it is acetyl bond O. Then you have another O. And after that, you've got a bunch of carbon atom. That's one carbon atom, two. So two carbon atoms after that. So that's one. You got another one. And then there is another O. And then there's a continuation bond. And on this side, you've got, on the left side, this side, you've got a acetyl bond O. And you've got this thing. So that's what they've drawn. And they've said that this is your repeat unit. So that means, as over here, there would be two hydrogens as well. I haven't added the hydrogens. Carbon should be making 4 bonds. So they should be. In the skeletal formula above, they don't show that. So anyway, so here's your molecule. And that's your repeat unit. So this thing is going to repeat. So I'm going to draw another one. And I'm going to make it repeat. And I'm going to connect the ends. So that's kind of fine. Now what you're going to do is you're going to find all the ester links or all the linkages. Here's one linkage. Here's another. Make sure, remember, don't try to find monomers by just looking at the repeat unit. Make sure at least draw 2 repeat units so that you're able to actually see the full picture of the polymer chain. Here's another. Here's another ester link. So what I'm going to do is I'm going to break all these. I'm going to break all these ester links, and I'm going to see what type of monomers do I get. So we're going to just do that. So we're going to just do that. So the ester links are gone, and I'll just get rid of these these side ones. I'm just going to get rid of these. So the ester links are gone. And the idea is that if you have a serial bond O, that is where the OH will fit in. Like this is where the ester link was. So if you've got a serial bond O, that would be a carboxylic acid. It would be double bond O and OH, and this would be an alcohol. This double bond O will be OH, and this one over here would be an alcohol. And same goes for this one. This one will have, it's got double bond O's at the ends. So that would be your carboxylic acid. So that's going to be your carboxylic acid. And you'll have, so you've got two monomers. One is a diol, and the other one is a dicarboxylic acid. And this one here is a so that's how this polyester was being formed. So by looking at the monomer, learn how to draw the by looking at the repeat unit, learn how to draw the monomers, and make sure don't try to figure this out by just looking at one repeat unit. At least draw two repeat units and then remove the linkages and figure out what the monomers are. So coming back to the question, let's go back to the question. All of these were biodegradable because polyamide, I mean, I'm going to write this down. This one is a polyamide. So the amide link is very, very polar. This one is polyester. And this one is also it's also a polyester. N number of times the ester links would. So they're all biodegradable. What type of polymer is this one? And what type of linkages does this have? Okay, what's the type over here? This one, remember, is an addition polymer because the linkages, there is no linkages. It's just a carbon chain. So remember, these addition polymers, which you've studied in AS as well, addition polymers are, so your addition polymers are not, so they're not biodegradable. Like if I have an addition polymer, so I'm just going to draw one very simple addition polymers. They're formed using alkenes. So addition polymers tend not to be biodegradable. Because the carbon chain is inherently very stable and it's non-polar. Like there are very few reactions in which you see carbon chains actually breaking. So addition polymers are not biodegradable. Carbon chain is stable. And one of the reasons it's very stable is it's non-polar. It's a non-polar chain. So one example is, I'm just going to draw one example of an addition polymer. You need a double bond for that. And the way the polymer is drawn is, okay, the first thing is you're going to redraw this molecule. What you're going to do is, if it's a but2-ene molecule like the one shown on the screen, if you have a but2-ene molecule, what you're going to do is redraw this. Don't break it. Just make sure that around the double bond, there should be nothing on the right side or the left side of the double bond. So what you're going to do is you're going to take this CH3 and you're going to bend it downwards. Here's another CH3 and you're going to bend it downwards. So I'm going to exactly do that. I'm not changing the molecule in any way. I'm just rewriting it in a different way. So the CH3 is pointing. Instead of pointing to the right, it's actually pointing downwards. Because in an addition polymer, it's a double bond that reacts with the other double bonds. They end up forming linkages. So you'll have lots of monomers, thousands of them, and they're all going to add up. The double bond would, so the double bond in the middle would break. And linkages would get formed between them. So that's a carbon link, a carbon chain. And the repeat unit is going to be, it's just this thing getting repeated over and over again. So that's basically your repeat unit. And finding the monomer is kind of really easy. Like if you're given the repeat unit, you don't really have to, like, you don't have to do what we did earlier. So if I'm just given this thing, all I have to do is, if I want to find the monomer, all I have to do is, if they tell me that this is the molecule, all I've got to do is just get rid of the continuation bonds. And they ask me for the monomer, just get rid of the continuation bonds, this N over here, and put the double bond back in the middle. That's it. That's my monomer. So this one, so this one is kind of easy. But remember, this is not that biodegradable. So for example, in this question, if they had told me, or they haven't told me, but if they had told me, how did I know that it's an addition polymer? Because the main branch, this one over here, that is undergoing, that is making the side connections. That is just a simple carbon chain, that's it. So that is definitely an addition polymer. Now the next part is, what if they give me this and I want to figure out what the monomer is? What I'm going to do is, so let's say they, one second. So let's say they give me this. First thing I'm going to do is I'm going to draw it in an easier way. So there's this carbon atom, there's this carbon atom, and then there's this carbon atom that's kind of at the top. So it's two carbon atoms. That's one. That's two. There's another carbon atom at the top. There are linkages on the sides. That's one on this side and one on this side. And then there's a linkage at the bottom. That's a carbon atom with a double bond O. And then it's actually an ester link and with a CH3. So, and you add in the hydrogens. There's going to be, I guess, 2 hydrogens with this one. There should be 3 hydrogens with this one. That's not you. So there would be 3 hydrogens with this one. So you bring in the hydrogens. And this is your repeat unit. So what did I tell you? How do you figure out the monomer? It's easy. Just draw the whole thing again. Get rid of the brackets on the sides and the continuation bonds, that's gone. And you bring in the double bond back again in the middle. That's it. So that is my monomer. TK. Is this clear? This thing? Is this clear?
Yes, sir.
So that's about addition polymers. And remember, they're not biodegradable. Addition polymers, I'll just give you some examples. Like, you should know that PVC used in pipes and tiles, etc. So PVC is this one. PVC is like a polyethylene, except that it's got the monomer is a polyethylene molecule repeating, except that there is one Cl that's substituted. So that is what PVC stands for. Polyethylene, that's another one. Polyethylene is your plastic bags, your normal everyday plastic bags. Those are polyethylene bags. So a lot of plastics basically are made from these ones, and so in polyethylene, all of them would be H atoms.
Sir, तो फिर ये recently we've been hearing ये biodegradability के ऊपर biodegradable shoppers आ गए थे market में. So what was I mean the plastic bags. So what were they made of? Yeah.
So they probably are polyesters or polyamides, not. I mean, like for example, paper is a polymer, right? Or tissue paper is a polymer, but it's very biodegradable. Okay, why? Because I mean, a tissue paper has polar linkages. So whenever you have a polar linkage, it's bound to react with something. So it's going to react with water. I mean, mostly it's going to react with water. So paper, like tissue paper, dissolves in water. As soon as you put it in water, it dissolves. It simply dissolves because it's highly polar. But addition polymers, these I mean, like your everyday plastic bags or plastic bottles, they're not that because they're very hydrophobic. They're non-polar. The carbon chain is extremely non-polar, so it doesn't really break. It doesn't. It's very hard to break it. And moving on, so that's the first part. That was just 2 marks. We just went through all the examples. Over here, he's asking, draw the structure of the 2 monomers used to form polymer B. We actually did that. I think we did that. We did draw the 2 monomers. Now we're seeing a section of the polypeptide was hydrolyzed and the following amino acids identified. Which of the amino acids TUV has the highest pH in aqueous solution? Explain why. TUV has the highest pH. I'll just quickly do polyamides as well, because that is also a type of proteins, basically. Proteins or polypeptides. Now the difference, they have the same amide linkage. Bhasgar, that's no longer. Group 4 is no longer in your course. I see. Well, proteins and polypeptides, same linkage as same amide link. But monomer is different. The monomer is so the monomer is the only difference is that the monomer is an amino acid. So that's an amino acid. What's an amino acid? It's a carbon atom, an alpha carbon that's attached to a carboxylic acid group on one side. So it's got double bond O and OH, and it's got an amine group on the other side, NH2. It's got some side chain, let's call that R1, and it's got an H at the top. So it's got an acid group, it's got a basic group, and it's like these are the 2 same things. And you have 20 different amino acids, human beings, etc., animals, different structures are made out of protein, enzymes, cells, your hair, your nails, everything is kind of made from. Now, the only difference between all these monomers is, all these amino acids is this R group. So humans are made out of like 19 to 21 different amino acids. And the same thing would kind of happen. The OH will be lost, the H will be lost, H at the end will be lost, OH is lost, H is lost, carboxylic acid loses its OH. And they would all, at the end of the day, join up to form amide or peptide linkages. So that's gone, that's gone, this is gone, this is gone, this is gone. And they will come together and they will join up. So they're going to join up. And it's the same amide link, which is now known as a peptide link. And hydrolysis reverse would happen. It can happen. Hydrolysis will happen. This side is basically condensation. And the reverse is hydrolysis. You can break a protein by simply heating with dilute acid.
Sir, the hydrolysis of amides will result in acid and amines, right?
Okay, so you're going to have dilute acid plus heat or reflux. So the whole thing basically breaks back into. So that's basically protein. So the only thing is they're going to ask you a lot, though our group would be different. For example, over here, in this question, they might ask you to draw the polypeptide. I don't know if, anyway, so that's your amino acid. I'm actually going to draw the polypeptide. Okay, let's start with the first thing. Which of the amino acids T, U, or V has the highest pH in aqueous solution? Highest pH means it should be alkaline, right? So it's got to be alkaline. And which one is alkaline? Remember, carboxylic acid group is acidic. Why is it acidic? Because it's capable of losing H+1. The NH2 group, on the other hand, is basic. I mean, we did the comparison of acids and bases. So that is basic because it's capable of accepting H+1 ions. So and there's a thing about amino acids, and that is that it's going to be V. Why? Because if I look at this molecule, look at it around here, this carbon has one H, right? It's got an NH2, the same carbon, it's got an NH2 on one side. And it's got a carboxylic acid group, not COOH, draw the whole thing. So it's got a C double bond OH. I mean, this has one NH2 attached to it, it's got an H, and it's got a carboxylic acid. And on the fourth side, it's got a CH2, 4, and an NH2. So it's got CH2. I mean, that's 4 times repeating, and then there is an NH2 as well. Now, this one has 2 basic groups. It's got 2 amines. It's got one basic group, and the R group also has a basic group. So it's got 2 basic groups, and they're capable of accepting H+9. So amino acid V is the one that's going to be more basic because it's got 2 basic groups. Is that clear? You clear?
Yes, sir.
And then it says state how many different dipeptides could be formed from a reaction mixture consisting of amino acids T and U. So how many of these can you make? You can make 2 of them. It's either going to be T plus U, or it's going to be U plus T. Both of them are going to be different. Like if I draw T, if T is first, it's going to be C. I mean, remember, order in amino acids, the order is important. If the order is different, if the first monomer comes and the second monomer is after this arrangement is different compared to this one, because the linkage is going to be formed the other way around. So I'm going to draw this one. I'm going to draw this one at CH. Let's just quickly draw this. You got a CH. and you got an NH2 and a COH. So there's a C double bond O, OH, and on the other side you got NH2. And in the bottom there is a CH3 group, right around this C with single H. So that's the arrangement. That's the first one. And V is this big one. It's the same structure. So you got a double bond O and OH, and you got an H, and you got NH2. And at the bottom there is CH2 4 times. And then there is an NH2. So what will happen is that the H and the OH will go in the middle. And there is going to be a linkage that would be formed over here. That's your dipeptide. So that's one dipeptide. The other one would be, I think this one is, which one is this one? I said they didn't even ask for this one. I made the wrong one. They were actually looking for T and U. I actually made T and V. So, correct me. This is actually T and V. But let's go with T and V. Is that clear? If V comes first, then this would come first and this one would come later. So the order is important. That would be a different dipeptide. Is that clear? Clear? Yes, no. Is this clear?
Yes, sir.
Yes, sir.
Yes, sir.
So the answer for this one would be 2. And polypeptides obtain.
Yes, sir.
They've got a high proportion of carbon and hydrogen in the structures, yet many are soluble in water. By referring to the structure, explain why. Because they're capable of forming hydrogen bonds. They've got amide links or peptide links. So which is extremely polar. This got a lone pair. That's the negative part. The H is positive. You got an oxygen which is negative. It's got lone pairs as well. So they're inherently water attracting and they can form. You can talk about very polar. So it's a very polar amide link. And you can say that it attracts water. It's capable of forming hydrogen bonds. So it's highly water attracting. So let's check at least the word explanation for this once again, the last part. And that is just hydrogen bonds. He's talking about the name grouped polypeptide. So basically he's talking about hydrogen bonds. I said this one was actually 4. So why did he ask us to repeat? We misinterpreted. We didn't interpret the question carefully. State how many different dipeptides could be formed from a reaction mixture consisting. So how many possible? So it could have been T with T and U with U as well. So that was 4 actually. We just did U plus T and T plus U. It could have been U plus U and T plus T as well. So there were actually 4 dipeptides that are possible if you have a mixture of T and U in a solution. Is that clear as well?
Yes, sir. Sir, last question, what was the second point that was in the marking scheme? Okay. Name the bond between O and M.
There's hydrogen bonds, and basically the 2 marks were, one was hydrogen bonds, the other one was between what groups? So he was saying that the peptide and water between the peptide and named group in the peptide. So basically he was looking for that the oxygen lone pairs. You could have, what you could have written was that you could have written was that that the oxygen lone pair, like the C bond O lone pair, was attracting H from the water molecule. Right? Is that clear? So named group in polypeptide and
I mean, each oxygen in the water molecule is attracting the H.
but it's an amide link, right? So the water has a very, very highly positive H. Okay, so it attracts the lone pairs on oxygen. So basically, the second mark was to explain in between which groups is the hydrogen bond getting formed. ठीक है, is that clear?
जी जी सर लेकिन वो तो ऑक्सीजन और हाइड्रोजन का भी हो सकता था ऑक्सीजन फ्रॉम वाटर एंड
we वो कह रहे
हाइड्रोजन
हैं named group, so it could be the other one as well. So it could have been this H positive attracting the lone pairs from water, right? So that could have been possible as well. ठीक है, let's wrap this up. We will just make sure we did go through most of this is basic. ठीक है, just they're not going to be a very detailed question on polymerization. It's gonna be, I mean, the notes, there's some stuff that's missing, which is related to zwitterions and electrophoresis. So we can probably at the start cover that first. It's just a very simple, because we're doing proteins and amino acids. We can quickly cover electrophoresis as well. But let's do that in the next class then. Okay. Chale everyone. Take care.
चलो okay sir Allah Hafiz. Thank you.
Allah Hafiz.
Thank you, sir. Allah Hafiz.
मेरा एक क्वेश्चन था
हाँ जी.
सिर्फ प्रोटीन्स और अमीनो एसिड्स को रिमूव नहीं कर दिए नए सिलेबस में से
नहीं देख लेते, चेक कर लेते. नहीं, उसमें बहुत कुछ रिमूव किया है. A lot of it has been removed because you're just doing very basics now. Okay, so a lot of it has been removed, but the basic protein structure is most likely still there. One second. One second. But we a reaction of amino acids basically. ठीक है. So हाँ, वो पहले ना previously there was a lot of bio stuff as well. Like you went into a lot of detail about protein, secondary and tertiary structures. That is no longer there. Local basics like two amino acids connecting together. That's it. ठीक है.
Oh, thank you.
So thank you.
Okay, thank you.